Okay, hello class. Book 3.5, yay. All right, so this one's called Vector Calculus, and we're gonna start looking, we've seen some vectors already. We're gonna turn ahead a couple different ways and look at them, multiple ways, and get deep in our understanding of them. But we're also now gonna do something called vector functions, which are super cool. And we'll get, like for instance, the picture on the front here is my attempt to draw a roller coaster. And this is actually a space curve. So we had been limited in R2 to functions that lived in two-dimensional space, right? And we talked about when we extended in book 3, what we were looking at there were surfaces over that. So again, right, a surface we created when we extended from y was a function of x to z is a function of x and y. Well, what's really neat this time, when we think about extending ideas from here, where again, just a two-dimensional curve, now we're going to go through three-dimensional space, the room that I'm in, and trace all sorts of curves. And that's going to be a function called a space curve. And we'll usually use r as a function of t, because we're going to think about this as you almost might say, like, what's the path that a fly would take over time? And so that variable t is, we'll have many instances, but often we'll think about it as time. And it's, again, the path that maybe a fly is tracing through the room over time. Historical tangent, which was how Descartes, we're not sure whether this is a true story or not, but Descartes was originally given credit for the Cartesian coordinate system after Descartes made this R3 extension by he was a sickly child and was sitting in his bed and watched a fly. He would spend much of his time in bed, watch this fly moving through the room and try to figure out the coordinates of it, and came up with the R3 coordinate system. So that idea of like watching a fly's path will get us also to think about space curves. We'll do a lot of analysis, but we're always, like usual, we're going to start simple. And in chapter 1 of book 3.5, we're going to start with, rather than curvy things through space, actually linear things through space. So we'll have lines, but we're not stuck in an R2 board. We can shoot that line now through three-dimensional space. And how are we going to describe that and define it? And then the other flat object we've already seen over here was actually a surface in 3D, which is a plane. So flat planes and straight lines. So those are the first couple things that we're going to meet in chapter 1. And then in chapter 2, we'll let them go as nonlinear as they want. Okay, so that's a quick preview. Oh, and then chapter 3, we'll come back to vector fields, which we did a little bit in book 3 with gradient vector fields, but now we're going to extend that to all sorts of vector fields. Okay, so in chapter 1, though, before we can get to some of these cool space curve things and lines and planes in R3, we need some vector operations. And again, we've already seen vectors. We're often going to talk about like a vector u and a vector v. We'll use this bracket notation. Maybe we'll have the vector 0, 1, 0, and the vector 1, 2, 3. And we know what those look like. We know how to plot them. We did that from book 1. And now what we're wondering are, we're wondering if these vectors, how should we add them? How should we subtract them? How should we multiply them? So we're going to have vector addition, subtraction, something called scalar multiplication, something called a dot product, and something called a cross product. Oh, and vector norms. So like, how long is v, and then normalizing a vector. Okay, so those are the vector operations you're going to meet in the beginning of chapter 1, and we'll work a few here. So, okay, so vector addition, like many things, is done component-wise, so it's really easy to think about this as u plus v is just doing it 0 plus 1, 1 plus 2, 0 plus 3, and we get this new vector. And now for my physics, astrophysics majors, you probably also learned how to do vector addition visually or geometrically with something called the head to tail method. And so maybe we'll do that just in R2. Let's look at just the R2 versions of these vectors. Let's say u is just 0, 1, and v is 1, 2. So I'll plot those vectors. If it doesn't say otherwise, we assume the initial point is at the origin. So the vector 0 in the x direction, 1 in the y gets me to there. That is the u vector. The v vector is 1 in the x direction and 2 in the y would get me to here. And that is the v vector. Now, u plus v, just algebraically, is 1, 3, which would be the vector 1, 3. I'll put that in dashes here. That is the vector u plus v. And then the head to tail method says you can take either one, but I could take u vector and I'll put its head, the point that it starts at the tail of v. So I'll shift that here. Because that's an equivalent representation of u, right? We're allowed to shift them. Those vectors just have a direction and a magnitude, but I can move them to have different initial points. And so if I wanted it to have an initial point up here at the tail of v, it would sit there. And then notice that u plus v is the initial and the tail point of those. So it is the sum. This is u plus v. And you can always do this vector addition visually or geometrically like that, but it gets a little bit harder in R3 to think about two vectors pointing in space and then moving one's head to the tail and then shooting diagonally across that. Notice that I also could have taken v and moved its head to the tail of u, right? So this is another representation of v. And u and v then create this parallelogram of which u plus v is the diagonal of that parallelogram. Okay, you can do vector subtraction very similarly. So I can just do it algebraically here. It's also done component-wise. So that'll be -1, -1, -3. And notice, of course, it matters. V minus u is different, right? Oops. V minus u would be 1, 1, 3. And also notice that that is just the negative of u minus v, right? And that can also be done visually as well. If I go back over here to my just two R2 vectors, the two components, u minus v, make sure we distinguish that, would be -1, -1. And that is the vector over here, -1, -1. Okay, so notice that you can also think about u minus v as u minus a minus v. And that gets you to the same place. And that brings us to this point. Scalar multiplication of a vector is also done component-wise. So if I have this these R3 vectors here and I wanted to get 2 times u, that is just 0, 2, 0. Let's say -3 times v. That is -3 -4, oops, -3 -6 -9. And let's look geometrically what those do. So I'll work on my R2 ones because they're a little bit easier. U was 0, 1, and V was 1, 2. Let's look at V. Here's the vector V. Let's say we wanted to do 2 times V. 2V is just 2, 4. And that just stretches V by a factor of 2. It shoots it out. If I did 1/2 V, that shrinks it. It would go 1/2 1 would be right here. So just this short little, I'll darken it, boldface it. This is 1/2 V. So V has some length. 1/2 V is half as much. 2V is twice as long, but they always point in the same direction. And then what does the negative do? The negative flips it around. So this would be negative V. V had this length. Maybe I'll see if I can, if blue shows up. That pen doesn't. This was the original vector V here in blue. And negative V just points in the opposite direction, has the exact same length. Negative 2V points in the opposite direction and goes even further. Okay, so we have some visuals of what addition, scalar multiplication, subtraction do. Oh, I should do the one visual of the subtraction over here in R2. Maybe I'll go ahead and get rid of this, clean it up a little bit. So the R2 vectors U and V, if I wanted to do U minus V, again, those are just component-wise, so it'd be -1, and let's look at that geometrically. 0, 1, here is U, 1, 2, here is V, and then this is minus V. So again, I can think about U minus a minus V. Or sorry, U plus. I think I said that wrong a little bit earlier. It's U plus a minus V, right? U minus V is the same thing as that. And the reason I want to write it like that is because that reminds me that this is V, this is minus V. Now I can think of it as just the head to tail with the parallelogram, move U over here. And then I'll be getting the -1, yeah, right there. So I will be getting the head to tail on the vectors U and minus V. Okay, so those are the first three vector operations, which are all component-wise is the key phrase. All right. Okay, let me add a couple more. I was going to go up to the dot product and cross product, but let me add a couple more to the these last two. They're not component-wise, but we have seen them before, and they're a little bit simpler before we get on to our dot product and cross product. Okay, this bar V bar, that stands for our magnitude, the length of a vector. And from beginning of book 3, remember that the length of a vector is the square root of the sum of the components squared. It's just getting a distance using the Pythagorean theorem. And so the absolute value notation, so the length of V, also sometimes called the norm. Some books will also use a double bar. We're going to use single bar for that. You'll see double bar sometimes in the linear algebra class. It is, again, the square root of the sum of the components squared. So 1 squared plus 2 squared plus 3 squared, which is what? 9, 13, 14, square root of 14. So that's how long this vector is. And of course, you can probably see just by looking at U and the way we plotted U here, U is already length 1. So 0 squared plus 1 squared plus 0 squared is 1. Again, easy to see that it is a unit vector. And, oh, right, so also I forgot, on this U plus minus V, this vector subtraction as a head to tail, this was U, and here is an equivalent representation of U shifted to the tail of minus V, and then U minus V is the parallelogram between, the diagonal between the parallelogram created by U and minus V, and that is -1, 1. Okay, so that's how you, again, vector addition and vector subtraction can be done visually and geometrically for lower dimensional space with the head to tail method, but we also want to make sure we know the algebraic component-wise definition because we can have Rn vectors We'll get to some of those applications later in this book too, in chapter 1. Okay, oh yeah. So back to normalizing our vectors, or getting the length of the vectors. So we know that v is longer than u just by looking at these values. But if we want to normalize a vector, again, nothing to normalize for u, it already is length 1, which is also makes it a unit vector in our vocabulary. If I want to do this, so if I take v divided by its length, so the last component here, that is normalizing it. It just takes v, it still points it in the same direction, it just shrinks it so that it has length 1. And that is just taking v and dividing it by its length. So it would be the vector 1, 2, 3, divided by the scalar square root of 14, which is done component-wise. And so that would be, you could write it a couple of different ways. Just saying, I'm going to multiply the vector v by 1 over square root of 14, which again is going to force it to be length 1. It might have been shooting out much longer, and I'll just chop it off. Or you can write it, distribute that inside. And the first way clearly shows that normalizing v is pointing in the exact same direction and has just been shortened because this fraction is less than 1. Value is bigger than 2 here. When you do alpha times v, where alpha is bigger than 1, it lengthens it. If it's between 0 and 1, it shortens it. If it's negative, it points it in the opposite direction. There's several activities in the beginning of chapter 1 of book 3.5 that will really help you start visualizing all these vector operations. Okay, those are again sort of the basic ones, the ones that have got these little squirrely brackets. And then the dot product and the cross product are a little bit more involved to compute them, but they also have really cool applications.